Hi. Actually, that was not what I intended by this title, and I see your interpretation of it, which is interesting. But that wasn't um, what I meant by this title was does the problem that you're actually working on make a difference? And the idea was that a lot of data assimilation is based around a sort of abstraction of the problem, and the stuff that we have been working on uses the specific structure of the problem that you're looking at to design the filter. And so that's what that was sort of the intention of this title. So can you all hear me okay? Is it all right?
Yes.
Is everything okay?
Yeah, I turned the mic off, so I turn it on just for. So during the, if there are
Just to
questions,
respond.
I will turn the mic on. Otherwise, I'll keep it off so that it. Yeah, is that?
And you'll send me a chat message if there are any problems.
Yeah, or
Okay?
I'll just sure.
Okay, well, I'm really sorry I'm sure you've all heard the sad story of my efforts to get a visa which failed. Anyway, yeah, it's very sad not to be there, but it's great that I'm able to at least give this piece. So this is going to be a tag team talk, and I'm just going to give the introduction and the overview, so the sort of philosophical motivation for what we're doing. Okay, so it all came from looking at Lagrangian as data assimilated into an ocean model to improve that the state estimation in that ocean model. So here's a picture where you can see on the left-hand side, you can see the tracks of an experiment. This is, I should say, credit this to Amy Bauer of Woods Hole Oceanographic Institution, as she let me use this picture. They were actually interested in this field experiment in finding pathways from the Mediterranean to the North Atlantic in an effort to explain why the North Atlantic is saltier than it should otherwise be, than it would be expected to be. And so these are tracks that you can see where the various instruments are put in with these blue dots for the blue curves and then the red dots for the red curves, and then the instruments are tracked. You can see on the right here a cartoon which sort of shows you what they're like. They're sort of pressurized to stay at a certain depth, and then you can see they have this sort of weight on the end which holds them down, and then there is a pinger, a sound source, which is anchored on the floor of the ocean, and then through triangulation and the sonar signal, they figure out sort of their position, and they record that then as they go along. And then they drop the weight, come up to the surface after so many months, and dump that information to a satellite. So that's how you get these tracks here. So they would be tracks thought of as fluid particles at a certain depth. There are slightly different sorts of instruments that are out there now. This picture is a picture of Argo floats. You might have seen Elaine show this picture where they go down for a certain number of days, and they profile during their descent, which takes about 6 hours. They then sit at a cruising depth. They then go further down at the end of that cruise and come back up to the surface and dump the information. Generally, they're interested here in the profiling and the salinity and temperature. And Elaine probably talked about this in her talk, but they throw away largely this information about the position at their cruising depth. And our claim is that that could be recovered. But it has to be estimated in this case because you don't have a locating device. This is a picture of a glider, which is the most modern device. Those are the ones that are really being touted right now and used extensively. They're slightly different. You can see here, if this is a nice, you go to the Ego Glider website, which shows you, sorry, these are what are gliders. Oh, I thought it was, let's see, I'm sorry, it's what do gliders work. So you can see in this little cartoon a glider going down, coming to the surface, dumping. So in this sense, it's a little bit like the Argo that can sort of propels itself. It's on a track. Okay, so you have an augmented state vector. The idea is that you just append the equations for the drifters to the equations for the flow field. So the XF you want to think of as being the solving the fluid equations, the ocean model, the QG model, primitive equations, or whatever. So the first equation, the flow equations, is essentially that. And then you append to that equations for the traces. So you might be putting in two floats, say, and they're moving along. And so XD would be actually two, each of them two-dimensional or even possibly three-dimensional. And they would satisfy the equations where you're getting the velocity fields from solving the XF. Okay, so you just augment the state vector, okay, which is somewhat critical. Okay, next slide.
Okay.
Okay, now Heider-Salmon's idea. Heider-Salmon was a postdoc who worked with me about 5-6 years ago, and he came up with this idea of, because the tracer advection equations are two-dimensional, because they would be low dimension, treating them in terms of the data assimilation scheme separately or in a different way. He was extremely optimistic in what he thought he could do. So his idea was that you would do particle filtering on the flow variables and solve the full Fokker-Planck equation for the traces. So that was a very kind of idealistic point of view. But the issue is really that the XF is very, very high dimensional potentially, but the XD is not that high dimensional. And you're doing the observations entirely in the XD variables if you're doing pure Lagrangian data assimilation. So the modified idea, which we started working with, and this is Elaine, Amit, and I. Elaine's name should really be on all of this, of course, but I just wrote the names of the presenters, so sorry I haven't done that credits very well here. But the modified idea then was to do an ensemble Kalman filter on the flow variables and a particle filtering on the tracer variables, which is basically some kind of approximation, presumably to the Fokker-Planck equations, effectively. Okay, so at least in calculating the prior at the data assimilation step. So that was sort of the basic idea that's been in the air for a few years, which was a modification of Heider-Salmon's idea. Okay, next slide. So the other problem, which Nara Teep, who will speak, realized was that parameter estimation in some sense had a similar form, right? And what he's going to talk about, just to be specific,
Chris, I think we have lost the audio again. Hi, Chris. Okay, so we are on the parameter estimation slide.
Okay. Okay, so the idea here is to estimate the forcing from the state observations. I'll leave.
Nope, the audio lost again.
Nara to explain.
No, we hear about 3
Exactly
words and
what.
then nothing. Hi, Chris.
The dimensions of the F and so on.
Nope,
Just take
nope.
this as an absolute.
Okay.
Says, yeah. So you can probably look at that and see what I was trying to say, that the Lagrangian dA and the parameter estimation have this common structure, that there is a high dimensional part and a low dimensional part, right? And you can see it on this slide here, which is which. And then you can, but there's a flip in terms of what is being estimated and what is being observed, right? But the basic split between high and low dimensions is sort of similar in the two problems, and that's what. And that's the commonality between the two problems. Pass to you guys, and then you can give your talks. Okay, so I'm going to make you a presenter now.
Okay, fine. Yeah.
Okay.
Okay. So Nara.
And I'll silence my microphone.
Okay. So Nara will go first, and then I will go. So Nara.
Okay. Okay. Let's start. As Chris mentioned, I have been working with him on this parameter estimation. So the aim is to be able to track and at the same time estimate the parameters. And we're going to do this in the context of two-stage filterings. And as you see in the previous slides, right? You want me to check if?
Just asking.
Chris, can you hear me? We want to use the ensemble to approximate the mean and covariance of this conditional probability distribution. And the idea is that we're going to use the ensemble and flow it by the flow model and use that ensemble to approximate the background error, background covariance matrix. But the update equation, we still use the common update equation. And there is a lot of technique to make this thing work, such as inflation and localization, in order to suppress spurious correlation from the distant states. Also, the localization also helps to increase the length of the covariance matrix, and that's one of the reasons that makes the method work well. And in the case of particle filtering, we use ensemble to approximate this conditional probability distribution based on the ensemble approximation. So in this case, there is no update equation for the xt, so the xt is not moved. Only the weight of these particles will be updated according to this important sampling, where we sample from this proposal density and update according to this update equation. And of course, when we do this, we already seen that then show that we can do the resampling to just focus our computation on the particle that fall into a high probability region and try to ignore those particles that fall into the that had insignificant weight. We just ignore those particles. And sometimes when we keep doing this resampling, we kind of lost sample diversity. This is called sample impoverishment. And there is some technique to deal with this technique, such as jittering and merging technique. I will not go into details for this technique because I want to focus my discussions on this parameter estimation. And this is just the cartoon version. You have samples at time, let's say t, and this observation is the red star. And next step, just follow by the flow model. it fall into here, evaluate the likelihood, and we kill all these insignificant particle with insignificant weight and just resampling this weight. Some of them will be duplicated and we go on to the next step. And this, I think I skip this one, but just want to point out this what happens. Suppose you have these particles, and the one in the middle is the one that have very large weight. And when you do sampling, you duplicate the particle which had a large weight, but you lost the sample diversity, right? So some technique had been proposed to kind of, at the end of the day, you just get this picture instead. And that's deal with the issue of the sample diversity. But what you want to make sure that the mean and the first two moments of this sample is the same as this one. So the paper in Nakano has a way to doing this. Now let's look at the experimental setup. So I'm going to use this Lawrence 96, which is 40 variable systems. And we try to approximate this forcing Fi. This is the same example that Jesse just showed. And the forcing vary with I only, but constant in time. And numerical technique used, we saw this with delta t time step. And say that the true parameters, the true forcings here is just this function. So I'm going to run the ENKF with the augmented state and doing 3,000 spin up run, and then used the next 6,000 particles in this experiment. So we.
Spin up. I don't know what that means. Spin up.
Oh well, I ran 3,000. It's like just try to avoid the particle to be in the transient state. Just allow everything to fall into the climatologies or the attractor first. Just like a Lorentz, yeah, right. Right, I mean, just Lorentz with 3 variables. Yeah, right, yeah.
I guess you only initialize one attractor.
Yeah, right. Yeah. And then, so we get the initial ensemble from that. Anyway, we're going to do the state augmentation, which is really intuitive technique, right? So I want to estimate X and F. So I just augment F into the state. But of course, the problem is that the F doesn't have any dynamic, right? So in this case, I will just use a persistent model, follow what Jesse and Tom and Luis did. So F at time t will be the same as F at time t plus 1. And the observation will be this one. So I observe only half of the nodes. And with this noise. In this case, I will also do a localization using covalent filtering technique. So this is different from the local analysis and LETKF. In the local analysis, you do the local analysis on each patch and kind of combine them, have a way to patch them back together, right? But in this case, I kind of smoothing the covariance matrix, kind of just make the covariance matrix look like more like a band diagonal, something like that. And this will also increase the length of this covariance matrix in general. So in this case, I assume that I have perfect forecast model scenarios, so no stochastic term. And the interval between these observation, I denote here by delta, will be the parameter, will be something that controls the degree of nonlinearity. So if delta is just delta t, which is delta t is just computational time step, the flow map from the flow map will be approximately linear system. But if delta is really large, normally it's shown that if it's larger than 5 delta t, then the flow map becomes nonlinear. So, I mean, if you observe things at really low frequencies, from this step to the next observation step, then the flow map is really nonlinear.
As long as the error is small.
Yeah. Yeah, right, of course, yeah, right. So, and here this result when I do ENKF with 50 ensemble, and this delta is just delta t. So we are dealing with the linear flow map here. And what you see here is actually as time 0, not 1. So this is the initial ensemble of the parameters. And then after you run, it's converged nicely. And if I sampling the parameters, in this case, the frequency I got it right, but I got the magnitude wrong. I mean, the initial guess. But if my initial ensemble for the parameters look like this, so in this case, both magnitude and the frequency was wrong, still the ENKF still works, so the parameters converge to the true parameter.
When you initialize when you perturb for the initial perturbation in parameter, you do the perturbation superimposed to
Yeah.
a periodic.
Yeah, right. Yeah, right. Yes.
So in a way, parameter known that as the form like
Yes. Yes. And now let's look at the nonlinear case. In this case, I take delta t to be 10 times the computational time step. In this case, you can see that it doesn't work at all. And even with, for both initial distribution of the parameter. So, given that this augmented technique does not work, so Chris and I was thinking, well, we should do something about it. And let's just skip that. And we come up with this idea of two-state filters. So the motivation is really based on the previous example. And inferring about the forcing failed for a long observation interval. But actually, if I look at the result on the state, the ENKF can still keep track the state very well, even if the inference from the state to the parameter is not correct. And so that, our case, that's mainly because when we run ENKF with augmented state, the observation increment is translated to the increment of the parameters based on the cross covariance between two of them, right? Between the parameters and the state. If that's not enough, then perhaps we might try to run particle filterings on the parameters, assuming a known state, and run the ENKF for the state, assuming known parameters. And
T-1?
why is that?
Theta bar T-1 in the equation.
Theta bar T-1? Oh, I'm going to explain what it is.
I don't understand it, but it's one part where you're talking about one step of the filter. What's,
Yeah, one step of the filters.
so what do you actually do?
Yeah, this is the equation.
No, but already at the idea level. Like,
Yeah.
So
So here,
we're at time, and we are at
Yeah,
observation
right.
n, and now we're going to go forward. So
right,
you,
so I'm going to take the mean of the state from the previous step and assume that's known and run particle
what do
filtering.
you mean known? So you take the estimates
Yeah,
of the
yeah.
parameter from the previous step.
Yeah,
Then you use that to update the
parameter only.
the state of the field given the known parameter.
yeah.
And then what? How do you update the parameter?
Actually, I do the parameter first. Okay, here is what happened. So I take the point estimate of the state from the previous step and assume that it's known, and then to update the parameters and use the particle filterings to update the parameter estimate. And then when I get the parameter estimate, which is going to be the distribution, like I run particle filtering, I take the point estimate of that, which is going to be the mode, and assume that the parameters is known. So I condition, when I run ENKF, I assume that parameter is known, and run ENKF only on the state, not the parameter. So, would that make sense? I mean, so let's say now at time t, right? I have the state estimate from the time t-1. I denote this by x hat here. And just forget about this equation for a little bit. You can think of is the way to, normally if alpha equal to 1, you just get this persistent model plus noise, but alpha doesn't have to be 1. And then you plug in that, you run the flow map, assume that it's known with the different parameter, and you use particle filtering to update the weight, to update the distribution of parameters. And at the next state of the filtering, we now still at the same assimilation time step. At the next state of filtering, I assume that this parameter is known based on this one. Yeah, yeah, it's a mean or the mode. It's a point estimate, yeah, for your distribution.
Best possible state
Yeah,
in
right.
the parameter space
Right.
for the shot that you did is the mean
Yeah, right.
among all the particles.
Yeah,
Okay.
and assume that it's known, and then just run ENKF, yeah, on the state, and just keep going like that. And okay, now the question is that, well, why do I have to use this model? Why don't I just always set alpha equal to 1 and just use persistent model, right? So set the bar is the mean, the mean, yeah, the mean, yeah, right. So the idea, well, if the mean of these parameters, the parameter is represented by the ensemble, right, particles. The mean of these particles that represent the parameter. So what I try to do here is try to shrink the particle toward the mean, particle that represent the parameter toward the mean, because, well, if I just use a persistent model like this, that's not disturb anything. We can run with, as Dan was trying to point out, if we use particle filtering to do the parameter estimation, this is a problem, right? You can end up with what is called sample attrition issue in this, and that's because the parameter particles always stay with the same set as our initial case. It doesn't move at all. It doesn't observe the space at all. So what we try to do is we could try to add this artificial random walk. However, this was proved in this paper, Lewin's West, that this is going to cause the over dispersion over time that can be considered as loss of information. So to address this problem, he proposed this, instead of using random walk, we can use this model instead. It's called trinket kernel. And normally this alpha will be chosen to be something a little bit less than 1, so that the sample now is trimmed toward the mean, and that account for the over dispersion. So I use this kind of update in this two-state filtering. So now let's go back. If I try this technique to the previous example, does it work or not? The answer is really no. And that's because, remember that in that example, the parameter space is 40-dimensional. That's quite large for the particle filtering. And that's one reason it doesn't work. So let me change the problem a little bit. Instead of try to approximate the forcing itself, I can parameterize the forcing this way and try to approximate these parameters, theta 1 and theta 2 here, and assume that the average known, F0 is known, because most of the time we know the average. And here, in this case, the true parameter is 2 and 40. This theta 1 and theta 2 is 2 and 40. And the initial sample, however, is sampled from this distribution. So the distribution that's centered at 4 and 20 and has this diagonal matrix, this covariance matrix. So let's see if the ENKF work or not, and if the two-state filtering work in this case or not. So this is the result when I run the augmented state with the ENKF. So what you see here is 95% credible interval, and what you see here in the black is just is the mean of the distribution. It's the mean of because yeah, we are running ENKF, so we use the mean. So it's a point estimate for the theta 1 and theta 2 here. So the filter stabilized, but it's converts to the wrong value. Here is a true value, 2 and 40. And that is with delta equal to delta t. So we are in a linear regime.
So in this example, which model are you using to
Propagate forward the parameter. The persistence of the one that you just showed.
Yeah,
Persistence.
yeah.
Okay.
Yep.
So it's a classical ensemble canal filter with the persistent model for the parameter.
Yep, right. So it failed. Now, this is the result when I run two-state filterings. So again, it's a linear regime. So 200 particles is used to run the particle filtering step, and only 50 particles is used to run the ENKF step. And in this case, it works nicely. The particle converges to the true value.
But the model propagated is not a persistent.
Yeah, it's not a persistent.
So we do not really know what is.
Yeah, I know, yeah. And, okay. And now I want to know just whether or not it's just a luck. So I run 50 different experiments using 50 different initial ensembles. And in this case, for the two-state particle filterings, so this is a mean, the point estimate, the evolution of the point estimate or the mean for 50 different experiments. So you can see that it doesn't really depend on how I get the initial ensembles. So it's always converges to the same, to the true value. But for the INKF, you can see it kind of could end up everywhere. So in this case, INKF doesn't work properly. So there's some time that it look like it work, but that would not be reproducible, right? Because
But this is because your parameter is very nonlinear in the way that the forces function.
yeah, right. So it's yeah, I know, yeah. So you cannot rely on, the update really rely on this cross coordinate between two parameter and the state, but it's non-linear, so you cannot just rely on using that only. That's why. So now let's look at the nonlinear regime. So this delta is now 10 times to the computation time step. And I forgot that when I run ENKF, I use the local length equal to 2. And the inflation, I just keep 1. And again, in this case, the filter doesn't work. It's stabilized but converts to the long value. But again, this two-state filtering work. So in this case, 450 particles are used in the particle filtering step, and 50 particles are used in the ENKF step. And these are similar pictures. I ran 50 experiments with 50 different initial ensemble. And in this case, look, the variance here, there's more fluctuation in the result that you could get compared with to the previous one when you run in the linear regime. So this is an ongoing work, and so I think there's more work to do in here, and the advantage of the two-state filtering here is that it could be more effective than just using the augmented state and run ENKF in the case that parameter cannot be linearly decayed from the state estimate only. And if you have the code, particle filtering code and the ENKF code, the modification is really small. So that's one advantage. But of course, it has the limitation that parameter space must be very small enough, I would say, because as you see in the case, as I pointed out, in the case that I try to approximate forcing directly without parameterization, it doesn't work because that parameter space is too large. So the future work is I would run more experiment and try to do it with the Lagrangian data estimation. And the last one is about information. Whether or not I can indicate the region interface space so that I can launch the drifter and get more information to do this parameter estimation. Given that my background comes from the dynamical system, studying Lagrangian coherent structures, suppose you have the flow, maybe look like this. Maybe this is a jet regime, and this is the circulation regime, maybe like this. If I'm able to extract this structure from the flow, from the velocity fields, could I use maybe should I launch one tracers into different regime or not? Right? If I don't know structure, I could end up launch tracer like this and miss this regime. And for this last comment, I just want to study whether or not knowing the structures of the flow can help me with the data assimilation or not. It may or it may be not. For example, you could use this structure to do the localization, right? Because if you want to approximate the, say, velocity field in this regime, the drifter here will not enter to that regime at all. So the localization would be not just the radius, could be this pattern instead. However, I'm not so positive about that because sometimes I kind of think that the reason that localization works because it really increased the length of the covariance matrix. That's the way that, I mean, it's not really about the structures. When you localize the covariance matrix, kind of increase the length, and that kind of increase the effective dimensional covariance matrix.
When you localize, you are decreasing the length of correlation because of the localization. You are cutting down the far distance correlation. Good. I mean, when you apply the Gasparicon function that you showed, I guess that you do it by, by scar product with the covariance matrix. And then this means that this is sort of, that law is a sort of inverse exponential. So the long distance correlation are cutting away. So the elements which are far from the diagonal are tend to 0.
I think we can, I'm not so sure, but that's my impression is increased length. I mean, you have the matrix. Let's just say and if you make it become diagonal, you get the full length, right? Yeah, it's low length, yeah. So.
It's not the rank of the matrix. Localization doesn't change the rank of the matrix. It changes the structure of the matrix. Spatial structure. It's not the rank. Yeah, exactly. It's not. Yeah, structure in the sense. Yeah. The rank doesn't change, or in principle it.
Normally the rank increases.
Yeah.
Okay, and anyway.
Can I ask you a question, Nara? Can you go back to your picture on the last slide? I know you said this is...
this one?
Yeah, I know you said this is ongoing work, so I was just wondering if you have any intuition for, but besides the one particle that looks
this one?
looks astray, it sort of seems to tighten up and then spread out. Do you have any sense of... So if you threw away the outlier, it looks like your estimator, or like your filter is sort of tightened till about 20 on that scale, and then it spreads. I just wonder if you have any intuition for that.
Oh, okay. Why is kind of converged?
So it looks like it's sort of converged, and then it spreads out, and then it's converged to a wider... I was just curious.
I have no idea. Yeah.
But you're adding artificial noise to the parameter estimates, right?
Yep.
So is that what you're seeing? Because normally, if you were to do this exactly, they should converge to a point, but you're adding noise, so they can't do that, right?
Right.
So is that the noise you're seeing?
Oh, well,
Artificial noise.
Right, okay.
That noise.
So after he sort of found it, then the fictitious noise is...
So what you should do is,
Right.
when he's rehearsed, you should start decreasing that
Right,
noise level.
right.
But I don't know how.
Yeah, I mean, I understand
Yeah.
that. I mean, like, after I get to this step, I should stop adding noise, just kind of use persistent model only.
Decreases slowly.
Yeah, decreases slowly, yeah. I know, yeah.
I don't know how slowly.
Yeah. I agree with that, yes. And what's your question?
If the noise is the reason that you get the spread again, why did you ever get close to convergence in the first place? So that's just sort of, my question.
Oh, well, I mean, because you resampling, right? I mean, when I resampling, I get this parameter instead. Even the noise spread, it doesn't spread too much, right? Yeah, the way the noise spread is, it decided that when you have this ensemble, it doesn't spread, it doesn't increase the variance, it just increase the sample diversity. That's the way it is decided, because it changed toward the mean somehow, right? Because this part changed toward the mean. It's changed toward the mean before I add noise. So yeah, it is decided to be that way.
So
So yeah, you have the sample. Right, right, yeah.
Yeah, I guess there's, sorry, the question of why you spread out again, or why you didn't just converge to that window that you see in the end. Yeah, I don't know.
This one or this one?
So can you just tell us, we were just wondering where you started the parameters. I just don't remember.
Oh, 4 and what? I forgot. 4 and 20, yeah.
And you started with a delta there? You started
No, it's with the, yeah, right. Sample from the normal distribution center at 4 and 20.
So
Yeah,
you
yeah,
talk
right.
around the real value, so it's unbiased your initial estimate. There is no bias in
the model.
If you take the mean of your initial perturbation, it coincides with the true parameter.
Mm-hmm.
So, no, it's because. That's why I say that.
Yeah. Yeah. 40. 40 is 2 parameters. I start at 20. Yeah.
My question is do you plan to use this, I don't know if I remember the name of this model that you used for the parameter, also for the propagation of the parameter, also in the context of ensemble Kalman filter?
Right, yeah. I plan to try that and see what happens.
And in relation to that, it seems to me a bit strange, the fact, because that approach essentially means that you are believing the mean, right? So you are forcing the particle during the propagation to converge toward the mean.
Mm-hmm.
But because so it is like that we implicitly believe that the mean is the maximum likelihood estimator. But maybe the reason why we do a particle filter most of the time is because we believe that this is not necessarily the case. So it's maybe it's a speculation of mine, nothing more than speculation. But I'm wondering if by choosing this propagation for the parameter, you are implicitly assuming then the mean is the best estimator by, which should not necessarily be the case.
He's giving one medicine, and then when that medicine has side effects, he's giving another medicine with bad side effects. Right? So if you just had a parameter being constant, which is really what's going on, the parameter is constant, right? Then the particle filter wouldn't work because there's no diversity, right? Mm-hmm. So he has to add noise to the parameter in order to get diversity. But when you add noise, suddenly the parameters go all over the place.
Yeah, right.
So then he's adding that extra shrinkage to the mean to sort of counteract these fluctuations that are coming from adding the noise.
Right.
So it's like he's giving one medicine and he's giving the next medicine to counteract the bad effects of the first medicine.
Yep,
But, I mean,
exactly. Yep.
it's sort of I don't know whether there's any principle behind this or whether this is just doing something and hoping for the best.
Yeah, you can look at.
I've never read that paper, so
yeah.
I don't know what the. But I think that's what's. Okay.
Yeah.
That's my guess anyway of what's going on.
That's the idea. Yes. Okay. Ahmed.
Switch to Ahmed.
Thank you.
Oh, thank you. Okay, good. So I guess this is kind of like a extension of, it's very related idea, set of ideas. Another proposal density, right? That's what large part of it will be. But okay, so I will, just to relate to Elaine's talk, I will start recalling the notation that we had kind of seen before, but let me just say this once more. So we basically have the prognostic variables, which are the velocities and maybe temperature, salinity, and whatever else, and the positions of the drifters, which will be denoted by xd. And then we combine those two into a state vector, which is the velocities and the drifter locations. And then the velocities evolve on their own, so the drifters do not affect the velocity evolution. But of course, the drifter locations are affected by the velocities. And so effectively this is, I will mention, okay, so let me jump to the next slide and mention a specific example. So for example, if you are using on one dimension, suppose your velocity field is one dimensional, and you are looking at velocities at the grid points, which are these blue dots. And so these are the velocity, so the xv vector will consist of velocities at its grid points. For example, VL, which will be velocity here, VR, velocity here, and so on and so forth. And if your drifter happens to be at the location xt, which is between these 2 points, PL and PR, then the velocity at the grid point is given by, say, a linear interpolation of the velocity here and the velocity here. So velocity on the left was VL, velocity on the right was VR, and that's a linear interpolation. And xt is part of the state vector. xv, which is VL and VR, is also part of the state vector, so you get a quadratic nonlinearity in this case. If you do higher order interpolation, you could get higher order nonlinearities and so on, but you have at least quadratic nonlinearity for sure in the velocity, in the interpolated velocity. Same thing happens for the spectral methods. If V1, V2, and so on are the Fourier components of the velocity field, then the velocity at point xd is V1, the Fourier component, times exponential of the Fourier mode, and so this is again a nonlinearity, not a quadratic nonlinearity anymore. But so in general, the model MD cannot be but nonlinear. Okay, so this model is the drifter model, dynamical model is nonlinear. The velocity flow, I will take it to be linear in this case, in fact, just the simplest possible case. So what we are observing are this is a general methodology in Lagrangian data assimilation or related problems, is that the observations are the locations of the drifters. So basically observing one component or some component of the state vector, which is xd. So the observation operator or this function h is just a linear projection onto a subspace of the state space and some noise added to it. Okay, so a specific example, so for the velocity model, I will simply take a linear shallow water equation model, very similar to what you are doing. It's effectively linear with no forcing, as simple as it can get, no dissipation, nothing. And because it's linear set of PDEs, I can simply write down a Fourier decomposition and choose as many modes as I wish without any modes mixing with each other. So I'll show results basically for these 2 modes. One which is a time independent mode given by U0 and a time dependent mode given by U1, V1, H1 for the velocity field and the height field, the same model that we have seen before. So even in this, okay, so we'll effectively reduce the PDEs to a set of ODEs for the coefficients, which are the equations here. And so we have 4 ordinary differential equations, linear, which you can write down the solution for analytically. And the drifters in this flow satisfy this set of equations. And remember, U and V are basically Fourier modes. So these are nonlinear equations. And in fact, they are chaotic, well, somewhat. So I'll show what kind of chaos they contain and so on. So again, exactly the same problem. The drifter positions are observed, which is S1 and S2, sorry, I switched to S1 and S2 because X and Y was becoming a bit too, X is the state vector, Y is the observation, so that's why I switched to S1 and S2 for positions of the drifters. And so we are observing the positions of the drifters and we want to get information about the flow, the full flow, which is basically in this case, these 4 variables as well. I will skip this for now. Let me just jump to the next slide where I have talked about it in more detail. So this flow, as I said, the flow is linear. The velocity field is linear. Only the drifter equations are nonlinear. In fact, the drifter dynamics has no, it's chaotic but Hamiltonian chaos. So if you know about it, you will see this very quickly. There are no attractors. There are some regions like the dot that you see here. Those are all chaotic regions. There are some regions which are regular trajectories. And it's a mixture of all of these in the phase space. So And that's a very peculiar feature of this model. So when you're asking for toy models, these are very nice toy models because they are quite different from the typical models that people use, which is Lorentz model and so on, which are the attractor. This one does not have attractor. This is quite a lot of rich dynamical features that it has. And okay, so these, sorry, I didn't get it. Yes, yeah. So these are, I mean, there are no asymptotically stable non-chaotic orbits. They are stable. Yeah, I mean, these are elliptic fixed points. So they are stable, but not asymptotically stable. But yeah, not asymptotically stable. So there are these KM-Tora, yeah. Okay, yeah. So, and then there are these unstable fixed points around which are the chaotic regions. Okay, so, okay, fine. So that I said all this before. And now, okay, so what am I doing? I want to basically show the effects of this nonlinearity on filtering methods in general. But what I will, the way I would do this is the following. There is, I mean, I basically use a MCMC method to sample the posterior distribution. So this model is deterministic. So I can sample the initial condition distribution on the initial conditions, posterior distribution on the initial condition, and then push it forward in time to try to get the posterior at the time of interest, at any time of interest. And in particular, I can also get the solution to the filtering problem by pushing forward the solution to the smoothing problem to the time that I want. And then I can compare that with any filtering method that I have. For example, ensemble Kalman filter, which is what I will show now. So what you see here is a few distributions. So let me, what happened to the captions? Okay, they went away. Okay, anyway, sorry. So I have to now explain this. I had this text here, which I don't know. Anyway, so the red, so okay, the picture is the following. I'm going forward in time. If I'm at some point where I have a distribution and I go forward to the next observation, so this is, let's say, T1, the first observation time, I go into the second observation time, I can push this distribution forward, but let's say by Fokker-Planck or particle, just solving them using particle methods or whatever. I will get a distribution which is just the forecasted distribution, and then I can apply a particle filter or an ensemble Kalman filter. In my case, I do actually a solution to the smoothing problem and push it forward in time and get the posterior at this time. And so that's what I'm showing here. So the magenta colors, so I forgot now which one. I think it's the black one. The black one is the distribution at time t1, which when pushed forward in time up to time t2 gives me magenta. So all the black dots here are at time t1. Magenta dots are all at time t2. So what happens is that, well, in the flow, in the velocity variables, of course, the flow is linear, so you start with something that looks kind of like a Gaussian. So it remains Gaussian, it spreads over, but it remains Gaussian. When you go over to okay, so sorry, this was U0, U1, V1, H1. So these are all the velocity variables, and these are the drifter variables. In the drifter variables, there is a high degree of nonlinearity, which is what gives rise to this non-Gaussian distribution function in the drifter variables. When you update using this drifter, so this is my prior, this is my posterior, this is my distribution at this time, and if I update now, I get the, I forgot which one. So since the captions disappeared, I think it's the red one. So say the red one is, yeah, oh no, so yeah, I'm right, yeah. The red one is the posterior after you apply the update. I mean, a reasonably converged particle filter will also give the same answer. In this case, this was obtained using a smoothing method, but wouldn't matter really. So this is the actual true answer, and I'm well pretty much convinced of it. So anyway, this is with something like about 100,000 to 500,000 particles. So the blue dots is the answer given by ensemble Kalman filter update. So of course we are observing the drifter position, And so the ensemble Kalman filter update in the position variables is pretty accurate, because that's what you're observing. That's good. But when you come to the velocity variable, the unobserved variables, that's where you don't see any effect whatsoever of the observation at all. And that's as expected, because in this case, if you take this ensemble and take a mean of it, it's right here. And its covariance is something like this. And so basically the ensemble Kalman filter has no information about the velocity flow from this ensemble of particles. And so the updates given by ensemble Kalman filter, which has blue crosses, are pretty much the same as the magenta crosses, which were the prior, and doesn't do anything to the unobserved velocity variables. And this keeps continuing, and that's what leads to the failure of ensemble Kalman filter explicitly. And so this is, so to say, one concrete example of what precisely is the dynamical origin of the failure of ensemble Kalman filter in this case. And this is not a, this effect is not a uncommon effect, and you will get a much better update. On top of it, if you make your prior much more concentrated, so that this blob, the black blob that you begin with, is much more concentrated, then also the effect of nonlinearity is much less pronounced. And so in this case, somehow the filter doesn't seem to be very stable, in the sense that if you change the prior, in particular the prior covariance, by sufficient amount, the ensemble Kalman filter does behave quite well. So anyway. But this is only the ensemble Kalman filter, not the exact filter. The exact filter is independent of the covariance of the prior. So I mean, as much as numerically I can observe. So, okay. So this is okay. I mean, particle filters, of course. So ensemble Kalman filter, fine, is a bad idea, right? So let's try using particle filters. But of course, they do still suffer from the problem of degeneracy of weights. So the weights, so to say, collapse onto a few particles, and you'll start losing. You have to do resampling and so on. And this is also bad for the chaotic system. So for particle filters, this is partly Elaine. I mean, basically Elaine was working on similar type of system, not this system exactly, the vortex, two-point vortex model and so on. But effectively what happens is the particles which have low likelihood are the particles for which the drifter trajectory is bad, poor, it goes somewhere far away from where the observation is, which in turn is basically because the velocity flow itself is far from the true flow. Because you're observing the drifter location, so you can correct it, but if the velocity flow is not close to what you actually have, then the drifter trajectory will not be good enough. And so somehow we want to add something like importance sampling step, where we want to sample the flow better by using the observations. But the flow is high dimensional, so we can't really do very well on this aspect. And so the proposal effectively is to use the ensemble Kalman filter update for the flow, because it's easy to do in high dimensional systems, but it takes you closer to the observations. But the nonlinearity, the high nonlinearity of the flow of the drifters can be captured by using the actual putting weights on the drifters. And so this is the idea behind this, behind the method that we are going to propose. Okay, the motivation came from this paper by Heather Salman that I guess Chris talked about, but we couldn't hear very well. So, and that Elaine mentioned anyway in her talk. So effectively, what you do is you split up the joint distribution of the flow and the drifters into two parts. You simply write it using the definition of the conditional distribution, and then sample, write approximation for the flow variable by using particles, but keep this conditional distribution exact. And so, I mean, this is approximation, of course, because this we don't know what it is, but so that's why there is an index I on this. For each different flow particle, there's a different distribution associated to each flow. And this is then can be, the whole theory can be carried through, at least the ensemble Kalman filter part of it. And he showed that it does lead to significant improvement in the results, because you are basically sampling the drifters in a very accurate fashion. And in the example that he had used in the paper, he actually solved a 2D advection diffusion equation for this exactly, and I mean numerically, but so it's a fairly high resolution sampling of that. And okay, so let me not go through the details right now. What we have done is, instead of, so if you don't really want to solve a 2D or 3D advection diffusion equation for drift of particles, the further approximation would be to also approximate this conditional distribution by particles. Oh, sorry, these particles. This is the flow part and this is the drifter part. And so effectively a picture will show this much better. So what you select is a few number of flow particles, because the dimension of XF is large, so you have only a few of these, but for each one of them you choose a large number of drifter particles. And so effectively you sample in the direction of the nonlinearity much higher, much better than the direction of the flow. And specific update proposal now becomes a choice that you have to make, and this is what I will show here. So this is basically effectively one important sampling proposal, right, in order to make the update. And so we basically update the flow particles. So think of, so these are the locations of the flow particles. XIF is the flow particles, right? So those are updated simply using the usual Kalman filter update. Except that we want to use something here which is the average of all of these dots, which is used for updating the flow here, right? And that happens for each of these particles. Oh, sorry, I guess this should be perturbed observation, so there should be YI clearly. And so this gives us a new ensemble. So these particles will shift somewhere else, but the weights will remain what they are. So we have a new, so to say, updated distribution for the flow. We haven't done anything to the drifters yet, but if needed, and I can usually say, oh, okay, not if needed, I guess you resample this distribution in order to get equal weight particles along this flow, along that direction, and now update the weights using the observation basically, right? And so this changes, this does not change the location of the drifter particles, but it changes their weights. And now you can also resample from that distribution to make them all equal weight. So at the end of the procedure, all these, so okay, the circles supposedly are proportional to the weight, but at the end of this whole procedure, these would have shifted somewhere, not shifted in that direction, but shifted only in the flow direction, and all of them will have equal weight. And so again, you start all over again and you go forward in time, and that's a specific proposal of important sampling intensity. Okay, so just some results using this on the same model that I had shown earlier are here. So these are the same variables U1, V1, H1, and a fairly long drifter trajectories. These kind of things cannot be really handled well at all by the smoothing problem, because if I want to do MCMC with this, okay, I have not yet managed, and it's anyway. Okay, so so the particle filter is shown in blue. The ensemble Kalman filter, the so to say the vanilla particle filter is in blue. The ensemble Kalman filter red. The hybrid filter, which I just described, in green, and the truth is in black. And so I mean, effectively you see that the particle filter also does not do so bad. In this case, the observations are quite frequent, and the particle filter and the ensemble and the hybrid filter converges. The ensemble Kalman filter does have some trouble, but if you wait for long enough, so U1 is something a bit weird. I'm not yet understood why that has happened, but anyway, it seems that it should converge, but I don't know why it hasn't converged. Anyway. And then when you take less frequent observations, I don't have the figure for less frequent observations. The things don't work as well for less frequent observations. And if you look at the errors long enough, then maybe we can understand something. So let me not dwell too much on this. And so effectively, what I presented was Lagrangian data assimilation as a sort of say unique system on which you can test many of these usual methods for assimilation, and many of them bring out this system really does bring out a lot of lacunae in the system quite well because of the peculiarity of the dynamics that you see. And you can understand the dynamical nature quite well here. Its Q product, the highly nonlinear part is the Lagrangian drifters, which is what is observed, and that is what suggests that you could treat them differently, the velocity flow and the drifter position, and that leads to the hybrid particle Kalman filter method that we just talked. And we are just trying to do this in a high dimensional model, not ocean model yet, but somewhere in between. And that's what we are currently doing. Thanks.
Where do you want to go first, high dimensional and linear, or still low dimensional and nonlinear flow?
I think the first thing would be to go high dimensional linear model, because in this model at least the main difficulty or the main nonlinearity comes from drifter. So even if you have linear flow, as I showed, right, you have highly chaotic and nonlinear dynamics for drifters. So introducing flow will not bring in much more qualitative differences, I think. But I haven't tried, so I don't know.
I think that's why we were sort of introducing the different possible weighting schemes. Because if the underlying flow is linear and you're just doing the translation, then it makes sense to hold on to the prior weights. But if the underlying flow is not nonlinear, then you'd like to somehow at least better approximate what you thought the posterior would look like. So maybe some important sampling for a nonlinear flow on that, in addition to the Kalman shift would be the thing to do. So probably the first test problem is linear in large dimension, and then nonlinear in large dimension.
The main reason for proposing only ensemble Kalman filter and not something more complicated for the flow variables is because in practice they will be very high dimensional.
Yeah.
You suggest that in general, also even if the original system for the system state is a typical chaotic, high-dimensional, chaotic dissipative system. So your proposal, your suggestion is more or less the same as NARA. So it's in a sense that as soon as you augment it, the system state either to estimate the parameter or, as in your case, because of the drift, you are adding a nonlinearity in any case, and this is better estimated through using a particle filter.
Using something that's more accurate than a ensemble Kalman filter or something like that. Yeah, exactly. Okay, hi Chris, can you hear us? Okay, I'll stop sharing the screen.
Yeah, I can hear. Can you hear? Yeah, thanks very much.
Oh, it doesn't want to stop sharing now. See? It's yeah?
Yeah.
Okay.
Just that was good.
Okay,
Very
great.
good.
So,
thank you.
yeah. Okay, so we will disconnect, or do you have any questions or comments?
We'll disconnect and then we'll just talk during the week, huh?
Okay, sure. Okay,
Okay,
bye.
thanks for all you've done.
Yes, yeah, bye.
Bye to everybody. Thanks.
Yeah, bye. Okay.